Hi, and welcome back to my Physics Online video lecture supplement series. Today's video we continue with the lecture set about electromagnetic induction. In the last video, of course, we looked at Faraday's law and Lenz's law, and in today's video I want to look at motional EMF, which is sort of an implication of Faraday's law, and then some applications of induction. In that previous lecture, we saw that there are three basic ways to induce a current. You can change the magnetic field's magnitude, you can change the area of the loop enclosing the magnetic field, or you can change the direction of the magnetic field with respect to the area vector, namely tilt the loop. And so all three of these methods basically change the magnetic flux that is passing through the area enclosed by your loop. One method that you can do one or more of these things is to move the conductor itself within the magnetic field. So I wanted to look at a few applications of this and a few sort of special cases, if you will, of this motional EMF. So the first one of those is motion-induced voltage, and for that we consider a single straight conductor, as pictured here, which is going to be moving through a magnetic field. The magnetic force acting on a given charge within the conductor, a given charge carrier, is given by this equation. Force equals charge of the carrier times the speed at which this conductor is moving times the magnetic field strength times the sine of the angle between the velocity vector and the magnetic field vector. This is basically just QV cross B, where V in this case is given by the motion of the conductor itself because the charge is within the conductor and therefore is moving with the conductor. Now, because electrons and protons or electron holes have opposite signs of charge, they will experience force in opposite directions. We actually looked at a similar case of this when discussing, for example, the Hall effect. What basically happens when you have one of these conductors moving through the magnetic field is that because the magnetic field force is in different directions for the two, you'll tend to build up positive charges on one edge of the conductor and negative charges on the other edge of the conductor. And so what that results in is an E field within the conductor, pointing of course from all the positive charges to all the negative charges. Again, just like in the Hall effect. When this happens, there are basically two forces which can act on any given charge carrier. One is the force due to the magnetic field, and it's going to be basically outward from the center of the conductor. The other is going to be the force thanks to the electric field that has been produced, which is going to be inward towards the center. Given that all the charges are basically along the edges, inward towards the center for a positive charge just means down. Outward just means up in this diagram, and then vice versa for the negative charges. What the force is from the electric field is due to this charge separation, and it's basically equivalent to the electric field which is produced in a capacitor, although it may have a slightly unusual geometry. For example, your capacitor might be the equivalent of a small plate here and a small plate here with a very large separation distance between the two. In any case, because these two forces are opposed to each other, at some point an equilibrium condition can be reached in which this force and this force have equal magnitude and opposite direction for any given charge. This condition is actually met when, again, the magnitude of the force for the magnetic field and the magnitude of the force for the electric field have equal size. They're basically equal, and they have opposite directions. The second condition, opposite direction, is true in any case, so long as you have this charge separation. The equal magnitude basically happens when you get sufficiently many charges on each edge of this conductor that the electric field is large enough to counter the magnetic field. That basically happens when the charge times the electric field is equal to the charge times the speed at which this conductor is moving times the magnetic field times a sine of theta in the event that it's not moving perpendicular to the magnetic field. And so if you divide out the charge, since it appears on both sides, you get E equals VB, again, times sine of theta if you're moving in some direction other than perpendicular to the magnetic field. Therefore, we can basically solve for the voltage drop by noting that the voltage from one end to the other is going to be the length from one edge to the other times the electric field. That's for a uniform E field, and again the E field is uniform because it looks kind of like a unusual shaped parallel plate capacitor. So what this means is that the voltage drop from one edge to the other is going to be E times L, which, since E is VB sine theta, would be BL V sine theta. So the voltage drop that you get for a motion-induced voltage between the two edges of this conductor that's moving in a magnetic field is given by the strength of the magnetic field times the distance between the two edges times the speed at which this conductor is moving through the magnetic field with times the sine of theta, which is the angle between the velocity vector and the magnetic field vector. Now let's consider this in another context. Suppose that you place this same conductor into a magnetic field as shown, but it's moving along a pair of conducting rails, which in turn form a closed loop on one end. Well, that means that you have a complete closed loop for this pair of rails and this moving conductor. Now, as this conductor moves, this closed loop's area is going to be changing. As pictured in this diagram, it's actually increasing. Well, that means that you're going to have a change in the magnetic field flux, assuming, of course, that the magnetic field is constant, or really assuming that it's not changing in such a way as to nullify by decreasing the magnitude of the field while increasing the area, or vice versa. So if the magnetic field is constant and uniform, then what you'll get is that the change in flux for the magnetic field, which is B dot A, is going to look like B times delta A, and so you'll get B times L times delta X, where L is the distance between the two rails, in other words, the effective length of this conductor that we've set up, and delta X is the distance between where the rail started, or where the conductor started, and where it is finished, or where it has moved to now. So that means that you have a change in flux, which is given by BL delta X for loop that is formed between the moving conductor, the pair of rails, and then the whatever you have connecting the end of the rails. According to Faraday's law, the induced EMF is going to be negative of the change in flux for the magnetic field per unit time. That is, the induced EMF looks like this. And so if we want an absolute value of the EMF, we could drop the negative sign if you prefer. Basically looks like delta of the flux divided by the time, so change in flux per unit time. And since the change in flux is the magnetic field dotted with the change in area vector, you basically would get magnetic field times length times delta x times sine of theta all over delta t. So we consolidate the delta x over delta t because that is by definition the speed at which this bar is moving. So that means that the induced EMF is the magnetic field strength times the length of the conductor which is moving times the speed at which the conductor is moving times the sine of the angle theta between the velocity vector for this moving conductor and the magnetic field vector. Again, in this particular diagram, because the magnetic field and the velocity are actually shown as perpendicular, the sine of theta term would be equal to 1, and so you just have that the induced EMF is BLV. And this is in fact consistent if we go up a couple slides to the motion-induced voltage. The motion-induced voltage delta V was BLV sine theta. That is in fact the same as the induced EMF that we're using down here for this entire loop. So it is consistent. Of course, if you have a closed loop, then you can actually get a current, and so the induced current will be the EMF divided by the resistance of the loop. So that looks like BLV over R times the sine of theta. This is the magnetic field strength. This is the length of the conductor, or really the distance between the two rails that it's sliding along. This is the speed at which it's moving. This is the resistance. And then this is the angle between the velocity and magnetic field. And you can use the right-hand rule in order to figure out the direction of the induced magnetic field. Again, point your thumb in the direction of the current. This is the thumb of your right hand. And then wrap your hands around the magnetic field, around the rail or around the conductor as if you are grabbing it. Your thumb points in the direction of the current, and your fingers will point in the direction of the induced magnetic field. There's actually two right-hand rules that go on here. That one's the second one, tells you which direction will the induced current be in. The first one is simply to tell you in which direction is the current itself being induced in. So you have the current is inducing a magnetic field. The current is being induced by the change in magnetic field flux. And note that if you're moving this bar in this direction in this diagram, these magnetic fields that are originally existing point downward. So you are, if we count down as negative, you are decreasing the flux through this loop because it is getting larger but negative. And so to counter that, you would need to have a magnetic field that is pointing up out of the page at you. If you move the bar in the other direction, then this magnetic field that's induced would need to be downward, and the current would flip directions, as would the location of both the positive and negative charge carriers here. Worth stating as well that basically what's happening when you induce this current is you move a charge carrier up here, and then instead of just ending up here, it has a closed loop to move around. Let's look at a few short examples now. All right, for the first one, we have an airplane which is flying from east to west with a given speed, and we have a wingspan, so we want to know what's the potential difference between the wingtips and what is the resulting E field magnitude across the plane. Now, before answering this, it's worth drawing a diagram here. So if the plane is flying from east to west, then the plane is basically oriented like this, and that is from west to east. The plane is actually oriented like this, and it is moving in this direction with a speed of 200 meters per second. And then if that is the case, its wings must be like this. So that would be basically north and south. And then here's the rest of the plane as viewed from above. There's usually like a little tail fin here, and then some guy like this. So where is the magnetic field here? Well, depending on where you are, the magnetic field, remember that the north pole is actually the magnetic south, south pole is magnetic north. So the magnetic field line might look like this, B, and here's V. If that's true, then what that basically means is that the force F sub B is QV cross B, and that basically means that the charges are not moving to the two wingtips, but in fact to the top and bottom of the wing. Okay, but that's basically the case if you're flying near the equator. We're going to assume instead that the plane happens to be flying over one of the two poles of the Earth. So if that's the case, then your magnetic field actually is more like this. And so V cross B means that you're going to have a charge separation such that you get some plus charges and some minus charges across the wings like so. So assuming that this is in fact the case that we have in this problem, then the question is, what is the induced voltage and what is the induced E field? Well, the voltage, delta V, you'll recall, was B times L times V times sine of theta. Well, sine of theta is 1 because this and this are perpendicular. And so delta V is going to be, we're on the Earth, so the B field is 0.5 Gauss, and that is 5 times 10 to the minus 4 Tesla. 5 times 10 to the minus 5 Tesla. So the induced voltage, this is a capital V, as distinct from the lowercase v that we're using for speed, will be 5.0 times 10 to the minus 5 Tesla times the distance between the two wings. These two wings are 25.0 meters apart. So 25.0 meters here times the speed, 200 meters per second. And so the induced voltage between the two wings, therefore, is going to be about 2.5 volts. So 2.5 volts is induced across the two wings. The second part is, what is the resulting electric field magnitude? Well, remember that delta V is E times L, or in other words, E is delta V over L. That again comes from the fact that E is actually delta V over delta X, where this is the voltage. So we have 2.5 volts divided by 25.0 meters, and so the E field magnitude must be 0.10 volts per meter. So now we want to consider the case of a bar which is sliding along a pair of tracks and is inside of a uniform magnetic field of 1 Tesla, and what we want is an induced voltage of 1 volt. Given that this is a 1 meter long bar, we want to know how fast the bar needs to be moving in order for this to be the case. Well, the induced voltage, or the induced EMF, is given by negative BLV sine theta. So what that means is that we can rearrange this equation to get what the speed V is from the induced voltage that we desire plus B and L and sine of theta. So if we do that, then what we get is that the speed is going to be the induced EMF divided by the magnetic field times the length times the sine of theta. And since we're just looking for the voltage, not the current or direction or anything like that, we can actually drop the minus sign from this if we'd like. This again is going to be 1 because the motion is perpendicular to the magnetic field. So what we have is 1.00 volts divided by 1.00 Tesla times 1.00 meters. And so what we end up getting is a speed of 1.00 meters per second. Now this is actually kind of a interesting and in fact to some extent important result in that it gives us now an operational definition for a Tesla. You'll recall that I previously discussed operational definitions for coulombs and amperes. Those basically came into play because you want to be able to have an actually measurable ampere or an actually measurable coulomb, something you can duplicate in the laboratory, and for those we used a pair of parallel wires. It's a more convenient definition than noting that one electron has 1.6 times 10 to the minus 19 coulombs and then trying to figure out how many electrons makes up a coulomb. This one right here gives us a definition now for Tesla. A Tesla is the magnetic field such that if you set up a bar on a pair of tracks, a sliding conductor on a pair of conducting tracks, that if you move this conductor at a speed of 1 meter per second and you get a measured voltage of 1 volt that's induced, then your magnetic field strength is 1 Tesla. Note that you don't necessarily need to have this track set up in order for that to happen, by the way. You can in fact just do this by moving the bar in the magnetic field with a speed of 1 meter per second. And if at that speed of 1 meter per second your 1 meter long bar has a voltage of 1 volt from end to end, then your magnetic field is 1 Tesla. So there is an operational definition for the Tesla. What I want to talk about next is transformers.
The transformers, more than meets the eye.
Suffice it to say that they play an important role in our everyday lives. Basically, you see here 3 types of transformer. One of them is pretty much an awesome cartoon from the 80s. One of them is a useful device for changing voltages so that you can move power from the power plant to your home. And the middle one is Michael Bay's attempt to ruin everybody's childhood. The electrical type of transformer, the one that we're interested in today, consists basically of a pair of coiled wires. They're called the primary coil and the secondary coil. And in fact, you've seen this setup before because this is the same setup that was used in Michael Faraday's experiment that I showed in the previous part of this lecture. These 2 coils may be interwoven with each other so long as they're electrically isolated from each other. They got to be insulated so that they don't have some charges jumping from one coil to the other. But more commonly you see them in this kind of configuration. There's a laminated iron core between them. The iron is there so that you can increase the magnetic field strength produced by the current in each of these wires. Namely, the current in the primary wire will produce a magnetic field, and that's what we're interested in. You want to increase the strength of that by using iron. The lamination is there to prevent eddy current loss, and of course you basically want the iron to not act as a conductor from primary coil to secondary coil. These are actually quite efficient. They typically exceed more than 99% efficiency. That means that more than 99% of the energy that you put in here will result in being produced over here as energy output. So if you put in 1 watt here, you should expect to see at least 0.99 watts worth out here if these 2 were otherwise equal. The more important thing is that the way that these work is that they change the voltage from primary coil to secondary coil and hence also the current. And so what happens is that you put in AC current through the primary coil, which means that you have a a continuously changing current and hence a continuously changing magnetic field. Since the current is changing, the magnetic field is changing, and therefore you're going to be inducing some EMF in the secondary coil because the magnetic field lines wrap like so. So there will be field lines from here into here. So the primary voltage is supplied by the power source typically. So this is usually to the power plant, or if you're near somebody's house, then this is from the power lines to the transformer, and then this goes into somebody's house. But oftentimes it's from the power plant to this coil, and then this coil is to the power lines. The primary voltage is coming from the power source, and it's going to actually be equal to the number of turns in the primary coil times the change in flux per unit time. So the change in flux per unit time is basically equal to the voltage from the primary divided by the number of turns from the primary. That'll be the change in flux for the magnetic field per unit time. Now, this B field, again, you can draw the field lines, will in fact pass also through the secondary coil. And so by changing the B field produced by the primary coil, you are in fact changing the flux of the B field in the secondary coil. And so that induces an EMF, which we represent by the secondary coil voltage, which is given by the number of turns times the change in flux per unit time. So the flux through the primary coil and through the secondary coil ends up being basically the same here. In fact, oftentimes this looks more or less like a toroidal geometry. Be that as it may, the result of this is that you can set up a ratio from the primary input voltage to the secondary output voltage. Basically, you just divide the two previous equations by each other, and you get that the ratio of voltages is equal to the ratio of the turns in each coil. So if you want to solve for how much voltage you'll get in the secondary, it should be this ratio, number of turns in secondary over number of turns in primary, times voltage from the primary. So if you have a step-up transformer, that's what's actually pictured here, there will be more turns in the secondary than the primary. That means that you're going to be increasing the voltage out. A step-down transformer goes the other way. There's more in the primary than the secondary. Now, energy conservation suggests that the power in and the power out should be the same. With that said, you can actually set it up so that the resistance in the two coils or in the two wires is different. If you put a large resistance in this wire compared to a small resistance in this wire, what are you going to get? Well, you're going to get less current in this wire for even a large voltage, or vice versa. Basically, energy conservation says that P is I times V, and so if you've increased the voltage here, you should be decreasing the current, or vice versa. Reason why that's so useful is because what you want to do is actually transfer power from your power plant over long distances. So here's how power transmission will work. Basically, power transmission says we generate power at our power plant, be it a dam, a coal plant, a nuclear plant, a wind power, whatever. And then you send that immediately to a step-up transformer. So maybe you get 12,000 volts out of the power plant, you step it up to 240,000 volts. Then you go through high voltage transmission lines that have very low current and therefore very little loss. The I squared R loss will be very small because the current is lower here. Then you send that into a step-down transformer substation. So maybe that steps it down to 2400 volts and then that goes through your normal power lines that you'd see sort of by your street. And then usually from there they go to a step-down transformer. That's the actual transformer that I pictured at the beginning of this discussion of transformers. Namely, this guy is the step-down transformer that goes from the 2400 volts that you're bringing in through these power lines into the 120 volts AC that you want at your house. So you step up from 12,000 to 24 or to 240,000. So that means there's 20 times more turns in the output than the input. You go through your high power lines, then you want to step down to 2400. So that means that the input has 100 times as many turns as the output. And then you step down further to 240. So that means there's 10 for the input for every 1 on the output. Or if you are in the US, usually this is actually more like 120 volts rather than 240 volts. In any case, that is the process of power transmission. So what was the first step in all this? It was generating the power. So that brings me to generators. How does an electric generator work? Well, it converts mechanical energy into electrical energy. That is what a generator does. And what it consists of is a loop of conducting material which rotates in a magnetic field. So here's what a generator might look like. Here's the essential thing in a generator. It is a loop, or a loop maybe of several turns, that conducts, that is placed within a magnetic field. And as the loop is rotating, the flux of the magnetic field through the enclosed area is going to be changing. That is, B dot A is going to be changing as this thing rotates because the angle theta is rotating. So this basically means that you're going to be generating an EMF and hence a current in the loop. That whole process sounds vaguely like it might be for an AC generator, although you can build both AC and DC generators. Here's what an AC generator looks like. You put a slip ring attached to each one of the ends of this coil. So this slip ring basically goes all the way around. It's in electrical contact with the end of just this coil. This one is in contact with the end of just this coil. And then each ring is in contact with basically what's called a brush. And so that's electrical contact. That means if, for example, you have current running this way as an induced current, then you get the positive terminal essentially is here, or the output of positive current is here. The output of negative would be here. And so current would come out, go through whatever you're trying to run, then come back in here, and you have a complete closed circuit. Now, why does this make AC generation? Why is this an AC generator? Well, basically the reason why is because as you rotate this coil, you're basically going to be decreasing or increasing, depending upon the orientation, the amount by which the flux is changing per unit time. And in fact, as you make a complete revolution, you will actually flip the direction in which the flux is changing. So for example, you're initially decreasing until you get to zero flux, and then suddenly you're increasing, which means that the current needs to be induced in the opposite direction, and then it starts increasing. Both the flux and the rate of the flux will be increasing or decreasing together. And so you end up getting an alternating current signal. And basically, because the magnetic field flux is B times A times cosine of theta, and theta is given by, if you think back to rotational kinematics, it is the angular speed times the time. It basically means that the flux can be given by BA cosine omega t, and the induced EMF from this basically would be change in this per unit time times the number of coils. So N, and then this right here is the change in this, BA omega sine omega t. And that is the change per unit time of this quantity. So NBA omega sine omega t is the induced EMF as a function of time. You can actually obtain that result by simple derivation, that is by taking a derivative. Recall that the induced EMF is negative N times d of the flux by dt. So that would be negative N times d by dt of, since the flux is given by B a cosine of omega t. You take a derivative of this. This and this are actually constant. So you're really taking a derivative d by dt of cosine omega t. And so your induced current should be negative N times B times A. Derivative of cosine is negative sine, so you'd get negative omega sine omega t, and so you have two negatives, hence this induced EMF is NBA omega sine of omega t. So again, the induced EMF is the number of turns that this coil that's rotating makes times the magnitude of the magnetic field times the area enclosed by the coil times the angular speed at which this is actually rotating times the sine of that angular frequency times time. That was how an AC generator works. Hypothetically, if you wanted to make a DC generator, you could do it, and they do make these. DC generator uses what's called a split ring commutator instead of a single slip ring. Really, instead of a pair of slip rings, since there's one for this side and one for this side in the AC generator. The split ring commutator is such that there's a gap in this ring. It still can make contact with the brushes, but at one point, namely when you're at a maximum amount of flux and hence actually a minimum amount of change in flux, there's a gap. And what that gap does is it allows it to switch sides. It allows the brushes to effectively switch sides. So this brush is basically taking from this coil for half of the rotation, and then during that half, this brush is taking from this coil, or this side of the coil. Then at the end of one half of a rotation, this end of the coil, which was previously producing this brush, will switch to produce for this brush, and vice versa. This one will switch to produce for this one. So instead of going negative here, you basically get your beginning of your AC signal, you get to 0, and then all of a sudden it switches sides, so the polarity actually stays the same. Then it switches sides and the polarity stays the same. Switches sides, the polarity stays the same. And so this basically is how you make a DC generator. The polarity never switches. The current is always running in the same direction around your load, even though the current is maybe running as an AC current in this loop itself. In other words, initially you would have the positive current maybe run like this, and then after it completes a half of a revolution, the current is actually running like this. That is inside of the loop that's in the generator itself, but in the part that actually is hooked up to a load, because these two are switching sides on the load, it never changes polarization. This is a DC generator, but it doesn't really show us what people usually think of when we talk about a DC signal. DC signal you usually think of as basically a constant EMF or a constant voltage. So how do you do that? Well, it's possible to get a steady signal for a DC generator, and the way that you do that is that you add more and more commutators and windings, because what that means is you can add many loops like this. So this is a loop, this is a loop, this is a loop, this is a loop, this is a loop. And so each one of these is hooked up to basically a split ring commutator. And so what happens is that while the change in this flux is very large, the change in this flux is small. This one's intermediate, this one's intermediate, this one's small. And as this thing rotates around, basically there always ends up being something near here, there's always something near here, there's always something near here. So there is some change because this thing rotates from here to here while this guy gets from here to here. But the change is actually fairly minimal, and so your signal basically ends up looking something like this. You still have, for example, a large change in the flux itself to generate this large voltage, but the change in the change of the flux gets to be a bit less, and so you get this repeating pattern like this. And as you add more and more of these loops and commutators, you get basically less and less variation in your voltage signal. And the way that that basically works is that each one of these loops is enclosing the same area A, and each one also has a different value for theta with respect to the magnetic field. And as theta is increasing for one loop, it's basically decreasing for another, and therefore the total magnetic field flux is changing, but at no point does the flux actually reach zero. And in fact, the change in flux basically never reaches zero. And so the result is that you get this nice smoother output pattern. So generators are nice for creating energy for like houses or for industrial use, etc. It used to be that they also used a generator to make current for an automobile, but they actually now usually use an alternator rather than a generator. And what this basically does is it avoids wear and tear from electrical arcing. So this is the basic setup of an alternator, and you can see that you have these are basically the magnetic field lines for North Pole and South Pole set of magnets. So these are kind of like bar magnets, and the North Pole is facing here, the South Pole is facing here, and so on. And what you do is you have an input current here. You basically rotate this guy. As shown, it would be clockwise if you're looking down at this direction. And you have all these little loops of wire in which current can be induced in your alternator. And then there's some output current that's been induced by having these things rotate around near these wires. So you're changing the flux in all these little loops of wire, and that basically induces your current. And basically these guys get used, for example, in automobiles. The sort of opposite of a current would be a motor. And the way that a motor works, I kind of discussed briefly in a previous lecture set, but worth touching on again here, is that it converts from electrical energy into mechanical energy. So whereas a generator is taking mechanical energy that's being put into basically making something rotate, or be it a loop that's rotating, or be it, in the case of the alternator, be it the magnets themselves that are rotating, you have to do some work to get that to happen. Well, a motor does the exact opposite. It takes the fact that you have some amount of current and electrical energy and some magnetic energy, and allows you to do some amount of mechanical work. here's the basic setup of that. You have a north pole and you have a south pole of your magnet. You have your loop of wire, and you're actually putting current through that loop. Now, if you put current through this loop, you're going to get a torque on the loop, and that's going to cause the loop to start rotating. And if the loop is hooked up to an armature like this, then it basically rotates the armature, and there might be like a gear or some such thing out here that's actually then doing the mechanical work on some system. And so the magnetic field is basically applying a torque because of the fact that it's applying force in two different directions, one for this wire and one for this wire, about an axis of rotation. And there's basically, again, a pair of brushes and split ring commutators, so that as this thing turns over, you basically flip the direction of the current so that the current is always going in the same direction with respect to the magnetic field. And so that means that the torque is always in the same direction. In this case, looking at it, we have a clockwise torque. And so every half rotation it switches to the opposite part of the split ring commutator. Hence, the current reverses direction with respect to the loop, but therefore, because the loop has also reversed direction with respect to the magnetic field, the current is in the same direction with respect to the magnetic field. And hence, the torque is always causing this thing to spin in our clockwise direction. And because this thing is rotating, it can then, by being attached to gears or what have you, do some amount of mechanical work. There's basically mechanical energy stored in this armature in the form of rotational kinetic energy. So I wanted to look at a few more examples here. This is really for a transformer and then also for a generator. All right, first a transformer example. We basically say that the primary voltage, V primary, is 12,000 volts. We're stepping it up to 24,000 volts. That's V secondary. There are 20 windings in the primary coil. That's N sub P. We want to know how many in the secondary coil, N sub S. Well, N sub S over N sub P, number of windings in the secondary over number in the primary, is voltage for the secondary over voltage for the primary. So the number of windings in the secondary is going to be this voltage ratio, secondary to primary, times the number in the primary. So that is 240,000 volts divided by 12,000 volts times 20. So this over this would give us 20. So that means that the number in the primary, the number in the secondary coil should be 20 times 20, or 400 windings. Now we're going to have a generator, and we need a frequency of 60 Hertz. Remember that omega is 2 pi times F, and the magnetic field B is 1 Tesla, and the enclosed area A is 0.25 square meters. And so the question here is, what is the maximum induced EMF? Well, the induced EMF in general is in BA, and we have a single winding, so N is equal to 1. So NBA times omega sine omega t. Okay, we want the maximum, so the maximum value for sine is 1. So max equals 1. So therefore, the maximum induced EMF is N times B times A times omega. So that would be 1 times 1.0 Tesla times the area, which was 0.25 square meters, times the angular frequency, which is basically 60 hertz times 2 pi. So if we multiply all these guys together, you get 30 times pi volts. So E max 30 times pi basically is going to be something like 94 volts. So that is what the maximum produced voltage for this generator is. All right, one more short-ish example. We want to derive an equation for the voltage produced by a generator as it begins to spin up. So the begins to spin up thing is because omega is going to be omega of t if the generator is initially stopped and later it's spinning. So here's the functional dependence of omega on t. And we want to derive some equation in terms basically of J and alpha and T and A and B. So we basically begin by noting that the induced EMF is given by negative N times d phi sub B by dt. So what is phi sub B given by? That's the key question to doing this derivation. Well, it was stated before that phi sub B, and this is just true in general, as long as you have a uniform magnetic field and a uniform area itself, but not necessarily a constant area vector, that you can use B dot A. So that would be B times A times cosine of theta. So basically you have a loop that has an area vector and it is within a magnetic field whose vector maybe is off at some angle. Theta is the angle between the area vector and the magnetic field vector. So area vector and then magnetic field vector is drawn here in green. I'm not very good at three-dimensional drawing, so you'll have to bear with me on that. And again, theta is going to be given by some function of omega times t. Theta you get by noting that omega is by definition d theta by dt. So that means that theta must be the integral of omega dt. Well, in this problem that you've been given, the omega, the angular frequency, has a specific functional form. So theta is actually going to be equal to integral 1/2 of j t squared plus alpha naught t times dt. So we do this integral, and what we get is 1/6 of j times t cubed plus 1/2 of alpha naught times t squared plus theta naught for what that's worth. We'll assume that theta naught is 0 to make this a little easier on ourselves. Okay, so this means that phi, the flux for the magnetic field, is B times A times the cosine of 1/6 of jt cubed plus 1/2 of alpha naught t squared. Now we can do this. Therefore, the induced E field is negative of N times d by dt of A times B times cosine of 1/6 jt cubed plus 1/2 alpha naught t squared. So that is the equation that we need. So now we do a derivative of this. And you'll recall that to get a derivative of all this, for one thing, these guys are both constant, so they can actually move outside of the derivative. If you want to do the d by dt of cosine of theta of t, you basically are going to get d by dt of theta times the derivative d by dt of cosine, or d by d theta of cosine theta. So what all this looks like, this guy right here should give us just simply omega again. This guy right here should give us negative cosine of theta. So collectively what we should have is that the induced EMF is basically negative n times a times b times negative cosine theta. So actually this negative ends up getting dropped, times omega of t times the sine of omega of t. And so it actually ends up working out more or less to be the same as before, except for that now this thing is E induced equals NAB times the function 1/2 JT squared plus alpha naught T times the sine of basically 1/2 of JT cubed plus alpha naught times T squared. So this is the functional dependence as a function of N, A, B, J, alpha naught, and T. Alright, so I wanted to give a brief summary of the new terms and equations that we used here. Basically, a conductor moving through a magnetic field is going to have a motion-induced voltage drop given by this equation. Delta V is BLV, and of course if the velocity vector and the magnetic field vector are not perpendicular, then it's BLV sine theta. Second of all, a loop whose area is changing, as in this diagram, thanks to the motion of a conductor, for example on a pair of rails with a total resistance here, is going to get an induced current. The current is determined by the right-hand rule, as is the induced magnetic field. The induced EMF for this is, again, delta phi b over delta t, as per Faraday's law, and that is going to be equal to BLV. And again, if this is at some angle with respect to the magnetic field, it becomes BLV sine theta. Then what's left in this lecture part is that we discuss generators, which convert from mechanical work into electrical energy. We discussed motors, which did the opposite. They converted from electric energy into mechanical work. And then we discussed transformers, which can be used to step up or step down the voltage using a primary coil and a secondary coil, such that the ratio of the secondary to the primary voltage is the ratio of the number of turns in the secondary to the primary coil. We did not, however, discuss them quite in this order. We talked about transformers first, then generators and motors. We also talked about the functional form of the expected voltage that a generator will output, but that is obtainable from this equation here. It is just a variation of this Faraday's law. It's not a variation of BLV, but it is a variation on Faraday's law. So that brings us to the conclusion of this lecture part, and in fact to the conclusion of this set of lectures on induction. So now I can roll the credits, And it's worth stating that we will have another set of lectures that have to do with induction that are actually pertain to what's called inductance. And we will talk about inductance and then about hopefully alternating current and basically a new circuit element called an inductor. And then we'll look at different circuit elements and how they deal with an AC voltage and an AC current, as opposed to the DC voltage and DC current that we've basically been using so far. So, hope you found this video helpful, and thanks for watching.